Welcome back, guys. So, last episode we left off on some introduction to proofs, where we talked about what a proof is, what it consists of, some questions to consider when solving proofs, what are mathematical statements, two types of mathematical statements, universally quantified, existentially quantified, what is a domain, what is the format of mathematical statements, symbolically. We looked at a couple examples like this, right? Um, and I believe that's where we left off. We also looked at how to convert mathematical statements from words into symbols. Well, today we're going to be focusing on logic and nested quantifiers. Well, what is logic? Well, logic is simply just we can consider logic as, well, kind of like true or false value. So if something is true or if it's false. So what is logic? What logic is like, does 2 equal 1? Right? So something like this. Does 2 equal 1? Well, from logic, we know this is false. I should say using logic, we know this is false. So logic is how you determine whether a statement is true or false. So determination of whether a statement is true or false. All right. So now let's dive deeper into what logic can actually represent. So firstly, there's something called negation. Now, what is negation? Think of negation as the opposite, right? So and this is actually represented by the symbol represented by, I think it's like that. Yeah. So it's represented by this symbol. Now, what does this mean? What is the opposite? So if I'm saying 2 equals 1, the negation would be negate 2 equals 1. And now what's the opposite of equals? So if we're trying to say the opposite of 2 equals 1, we could say 2 is not equal to 1, right? And we can say this because we're trying to find the opposite, right? We're trying to find the opposite of this statement, right? So if we're trying to find the opposite of 2 equals 1, what do we get? Well, we know that the opposite of equals is not equals, right? So we get this. And now if I'm trying to say the opposite of 2 is greater than 1, so negation of this. Well, the negation of this, right? Well, what's the negation if something is not greater than another number? Like if one number is not greater than another number, then, well, there's two cases, right? Either 2 is less than 1 or 2 is equal to 1. And how could we represent this? We can represent this as 2 is less than or equal to 1, right? And using this notation, we know that we can rewrite that the negation of 2 is greater than 1 is equal to 2 is less than or equal to 1. And now similarly, the negation of this would give you this statement, right? So realistically speaking, using this logic that I just explained, that if I have this and the negation of this is equal to this, and if I negate this, then I get this, right? So let's practically try it out first. So if a number is not greater than, if 2 is not less than or equal to 1, right? So if I'm trying to negate this and 2 is not less than, I'm trying to show that 2 is not less than or equal to 1, then what are the options for 2? So a number can either be equal, greater than, or less than. Here we've covered 2 cases. So cannot be greater than, cannot be 2 is less than 1 or 2 equals 1. So what's the remaining case? Remaining case is 2 is greater than 1, right? Well, if we have this was our original statement. This is our negation of the original statement, right? So basically what we're trying to say is that if we negate this, we get to this statement. And this statement, when we negate it, we get back to this statement. So it's kind of like a loop. So using this logic, we can say for some statement A, right? The negation of the negation of A is equal to A. This is called double negation. And if you have a tough time, if you have trouble understanding this, if you have a tough time understanding this, let's say statement A. Let's say A is, I will shop today. Okay. Negating this, we get I will not shop today, because it's the opposite, right? And well, and then now if we take the opposite of this, I will not, not shop today, right? Well, this means that you won't shop, and you're saying I will not shop. So that means that this cancels out and gives you I will shop today. So you get back to your original. So that's what a negation is. Now we can apply negation to what we looked at last week. So let's take a look at what we looked at last week, right? Well, what did we look at last week? We looked at for every positive integer n, right? This is universally quantified and existentially quantified. There exists, right? Well, now let's take a look. So let's take a look at first universally quantified statement, right? So I'm going to say negation for quantifiers. So we have 2 quantifiers, if you recall from last class. We have for all x in some domain, right? And we have there exists some variable in whatever domain, right? Well, what does this mean? This means for all, which means every single, right? This means there exists, which means some or a particular, right? Well, think of it this way. So negation of for all means you're just taking the negation of this. Well, what's the negation of this? If you're not taking every single element, so think of it this way. I have a box full of balls, right? I have different balls in here, right? And if I'm not taking all of them, my opposite would be taking one of them, or maybe 2 of them, or maybe 3 of them, but not all. All but one, technically. Like any but one, right? Which is the same as saying I'm taking some particular element from it, or there exists an element that I'm taking from it. So realistically, this is technically just this, right? right? And now, similarly, if we have the negation for there exists, well, if there's a negation for there exists, right? Think of the ball example again. There's a couple balls in here, right? Right? So there's a couple different balls in here, and if I'm not taking one, or if I'm not taking like a particular one from it, or a particular subset of it, or if I'm not taking like maybe one or two or certain amount from it, what's the opposite of that? I'm taking all of them, right? So you can say the negation of their existing is for all, right? And a way you could also show this is that, well, we know that the negation of a negated statement is equal to the original statement, right? So if we know that E is basically just negation of this, right? So negating E is equivalent to just taking the negation of for all, right? Which is the same as saying for all. So that's like a way to prove that this is equal. Now, one thing I have not mentioned yet, and that is you cannot, although I have written it here, this is not proper notation. Saying equals this statement is not proper notation, right? Because two statements technically aren't equal, right? For example, if I have say 2 is equal to 1 and 3 is equal to 1, are these statements, are they equal? No, they're not. But are they logically equivalent? Yes, they are. And why are they logically equivalent? What is logical equivalence? So now we're going to move into that. Logical equivalence is where two statements have the same truth value. Now, what's a truth value? Truth values are either true or false, right? So in this case, when I said that we have 2 equals 1 and 3 equals 1, right? Well, we know 2 equals 1 is false because it's not equal, and 3 equals 1 is false, right? They share logical equivalence, being false. Logical equivalence, right? So if I'm saying this, right, I'm basically saying 2 equals false, 3 equals false. So they're the same logical equivalence because they're both false, but these two statements are not the same, right? Now let's look back at let's go back to some of the quantifiers and proper mathematical statements, because quantifiers are just one part of the mathematical statement, right? So a mathematical statement in existentially quantified would look like this, existentially, right? And universal. These are our two types, right? So if we have something existentially quantified, and we're trying to negate it, we would have something that looks like a little like this. And let's say that this is, let's say D is our domain, right? And such that P of X is our open sentence that we're trying to solve for, right? Now, we cannot say that it's equals, right? Because we acknowledge that they're not the same statement, but they're logically equivalent. Well, how do you express logical equivalence? Logical equivalence is denoted by, it's similar to equals, but there's 3 lines. So I can't say that that these are 100% the same by setting them equal, but I can say that they're logically equivalent. And by this, I can show that they have the same truth values, but they're not the exact same that they're not the exact same statement. Well, how would we actually take the negation of this? Well, we know this, right? We acknowledge that if there exists an x, the negation of that would just be for all, right? So for all x in D, we don't have to change anything else there. Now we can take the negation of p of x. Well, what would this look like? Again, this goes back to right here where I was explaining, right? So if our p of x in this case is 2 is greater than 1, our this would be like our negation of 2 is greater than 1 would be logically equivalent to saying 2 is less than or equal to 1, right? So so negating your open statement would look something like this, where you change either the equivalence or like the sign or something where it makes that statement what you had before the opposite of your current statement, which would be your negation. All right, and similarly, if we try to do it with the universal, right, we get, again, we know negation of for all is there exists. So we get there exists an x in domain such that negation of p of x. Again, I explained what the negation of p of x would be, right? Now what we can do is we've mainly just been focusing on one variable, right? We only have one variable right here. What if we have a combination? Can we have combination? Can we have multiple variables? And the answer is yes. This is how that would look like. So if I had a statement with, say, two variables, x and y, right? So for all, let's say that this is my statement. There exists a y such that x is greater than y. Is this the same as saying, no, they are not the same. Because order matters, right? The order of your quantifiers definitely matters, because it's not the same as saying these two statements. So let me give an example, right? So if I consider this, right? So I'm saying that for all x, right? So that means that every real number x, every real x, there exists a y such that every real number will have at least one y that is less than x, right? Here I'm saying there exists a y such that it'll have every real x to satisfy this. Now you might think, what's the difference? I don't see any difference. Okay, so this is saying if I choose any x in real numbers, there will be a y such that this is true. This is saying there exists a y such that every x will satisfy this. So it's like saying I have, say, any list, and I can pick any element from that list, and it will be true for some y. And this is saying there's some y, there's only like a particular y, such that every x will be true. So this is saying for every x, there's going to be a y that's true, and this is saying for only a particular y, there's x's that will be true. So these are not logically equivalent. You cannot state that they're logically equivalent, right? But again, you can take the negation of these statements similar to how you would do any other statement. So let's try taking the negation of this one. If we try to negate this statement, right, we can split it up into negation of this statement, right? Negation of this statement, and negation of this statement. Well, what's the negation of for all? Well, we know that that's just there exists an x that's real. We know that the negation of there exists is for all y. And we know that the negation of x is greater than y is just x is less than or equal to y, because we just change it and make it the opposite. So this would be the negation of this statement. And this is logically equivalent to saying the negation of for all x that are real numbers, there exists a y in the real numbers, such that x is greater than y. These are just logically equivalent. Okay, so summary of this part is that the order matters when dealing with when working with multiple variables. So you have to be careful of the order of the quantifiers because a small mistake can cause many errors. And again, we discussed the how you can negate them, just in case you ever need to do that. And a couple things to keep in mind, obviously, are the order. It also, these domains could be different. If I have a statement that looks like this, right? And then say x is greater than y, right? If I have something that looks like this, technically I could say that in this case, I could say this is equivalent. I could say that they're the same in this case. And the negation, I could also actually write this as x comma y is an element of the real numbers such that x is greater than y. Or I could also say this. These are all the same. These all mean the same thing, just because their quantifiers are the same. That's why I can group them like that. Otherwise, I wouldn't be able to group them because they have different quantifiers. Okay, so now we're going to dive a little bit more deeper into logical analysis. So recall, this is negation, right? We discussed negation. Now, I'm going to go over conjunction and disjunction and truth tables in this class, and then next class we'll move more into implications and if and only if, because those are a little bit more complicated and those require a little bit more time. So truth tables are just tables of true/false values, depending on the case, right? So it's like saying when something is false, something is true or false, another is true or false, what is my output? Is it true or is it false? So what does this exactly mean? It's like saying this, right? I have two cases, right? So say I have a statement A and I have a negation of A, right? And then I have, let's say, the negation of A, right? Well, A could be two things. It could be either true or false. Well, we know that the negation would just be the opposite truth value, right? Because we're taking the opposite statement, so it would be the opposite truth value, right? Negation means opposite truth value because it's the opposite statement, right? So if it's the opposite truth value, that means that the true becomes a false and the false becomes a true. Well, now if we negate this, we get the false becomes a true because we're taking the negation of this, and the true becomes a false, right? Well, we can see that this column, right, and this column are very similar. In fact, they're the same when it comes to truth values, because when A is true, negation of A is true. When A is false, negation of A is false. What does this tell us? Like, when would I ever need to use this? What does this mean? This gives us our logical equivalence. So this is saying A is logically equivalent to negation of A. And the reason for this is because their truth values are the same when it's the same case. Now, how could we use this in other situations? For example, if we have a compound statement. Well, what would a compound statement be? Well, there's two things called conjunction and disjunction. Conjunction means two statements, and they're going to be separated by an and, which means both need to be satisfied. Both need to satisfy, right? So what does this mean? Which means A and B. So let's say that A, B are statements, right? So it's like saying it will rain and I will play outside. So in order for this to be true, it has to rain, and I have to play outside. That's the only time it'll be true. Because even if I play outside, technically the first requirement isn't met, so it's not true. And if it rains but I don't play outside, then technically one of the requirements is not met. That's why it can't be true. So what would this look like? Let's say that these are two statements, A and B, right? And then what is A and B? Right? So when A is true, B could be false. When A is true, B could be true. When A is false, B could be true. And when when A is false, B could be false. So these are 4 situations. You write out all the permutations possible for it. So if A is true, B could be true. If A is true, B could also be true. If A is false, B could be false. Or if A is true, let me reword that. So here are different cases. So we know that if A is true, B could be false. We know if A is true, B could be true. We know if A is false, then B could be true. And we know if A is false, then B could be false. These are 4 possible combinations for it. Now, what about A and B? So if A is true and B is false, right? So that means that one is true and one is false. Well, if it rains, but you don't go outside to play, then this makes this sentence false because both must happen in order for the statement to be true. So that means you get false. Now, say it rains and you do go outside to play. Well, then this statement becomes true, right? This becomes true, right? So you get 2, true. Now, it doesn't rain, but you go outside to play. Again, both of them have to happen in order for it to be true. So you get false. And again, you don't go outside to play, and it doesn't rain. Well, the statement was, it will rain and I will play outside. You're very certain about it. But if neither happens, then it's still false. So this is what your truth table for a conjunction looks like. Well, what's the notation for conjunction? Because as mathematicians, we don't like using and. We don't want to use that. We use a symbol that looks like that. It's called a caret, right? And this is how you'd use it. Not sure if this is the upside down one or the right side up. I think this is the upside down. No, this is the proper caret. And then I'm going to go into the next one, which is going to be the upside down caret. Well, this is what a conjunction is, right? Now let's talk about disjunction. Right? So now we have disjunction. And what is disjunction? Disjunctions are 2 statements, right? Again, I'm using 2 statements here, but it could be between multiple. So you could have you could have like say 4 statements where you have A and B and C and D, something like that, right? But for this case, just to explain the concept, we're only going to consider 2 cases. So we have 2 statements, right? And here it's A or B has to satisfy. So what does this mean? This means if either or, so either or. So let's consider our example again. So let's say A and B are statements, right? And let's say our old statement, except this time it's or. So I will play outside. It will rain or I will play outside. Play outside. Right? So I have this, right? Well, now I know, again, A, B, and A or B, right? Now I know this. So again, A could be true, B could be false. A could be true, B could be true. A could be false, B could be false, and A could be false, and B could be true. These are 4 possible situations. Well, in this case, right, it will rain, but I do not go outside to play. But my statement says it will rain or I will play outside. So it doesn't matter which one's true, as long as one of them's true, it would be true. Both of them are true. So it will rain and I go outside to play. Well, again, it will rain or I will go outside to play. One of them is met, so this is true. Now in this case, it doesn't rain and I do not go outside to play. So none of my conditions are met, which means it's false. And again, in this one, I go outside to play, but it doesn't rain. But that doesn't matter because one of the conditions are met. So, again, and now we can take a look. We can see a pattern here. So look, if you look up here, right? When A is true, B is false, the overall condition is false. Here, if A is true, B is false, it's true. So it's the opposite. Okay, well, let's keep going. Here, if A is true, B is true, right? If A is true, B is true, then A and B is true. Here, if A is true and B is true, then A and B is true, or A or B is true. Here, if A is false, B is true, then A and B is false. Here, if A is false, B is false, then A or B is true. And last case, if both A and B are false, then if both A and B are false, then A or B is false. And here, it lines up. So, in either of the situations, we know that if they're both the same value, it's going to give you the same, truth values. Oops. Right? So if they're both the same truth values, right? So if both statements are the same truth values, you're going to get the same value out of it. But in the other cases, like this case right here, in this case, and over here would be, this case and this case, you get opposite values. Because here you get true, and here you get false. Right? So in this case, we can say, oh, hold on. I forgot to mention the notation for, so the notation for disjunct is equal to this, right? Here it was the one that's facing down, here's the one that's facing up, so it looked like this, right? And you can, again, the same rules apply where you can have multiple. So if I had 4 statements, it would look something like that. Now, where was I? This and this and this and this. Consider these 4 cases. It's the opposite truth values. So we can say negation of and is logically equivalent to or. Now, using our double negation, right? Since we know that this is equal to that. So now if we try negating this, we get that it's logically equivalent to the negation of or. And then from this, we get or. So the negation of and is or, and the negation of or is and. Great. Now, there are a couple of rules when it comes to using logical operators. Let's discuss De Morgan's laws, DML for short. Consider that I have 2 statements, right? I have 2 statements, A and B, right? If I'm trying to find the negation of A and B, this is the same as saying I find the negation of A, find the negation of and I find the negation of B. Well, we know that we don't know what these statements are, so this is left in general form until you have a specific example, but we know what this is. We determined that the negation of and is or. So this is equivalent to saying and negation of A or negation of B. That's the same. And now similarly, we can say the negation of A or B is logically equivalent to the negation of A, right? Negation of or, negation of B, which is the same as negation of A and negation of B. Now, how do we know this? Well, if you want, you can make a truth table, just like we did right here. So it would look something like this. It would be A, B, negation A, negation B, and then you do negation A or negation B, and you do the same thing for and you can show that that this statement. So then you can also find like this part, right? Make a truth table for that, and then negate all of those answers, and then you can create one for this part right here and show that they're equal. Unnecessary though, because we know that De Morgan's laws hold, so we can just apply them and refer to them whenever we require. Now we also have commutative laws, right? Which basically state that the order of statements does not matter. Order of quantifiers definitely matters. Order of statements between conjugative or disjunction does not matter. So between conjunction and disjunction, the order does not matter. But when you have quantifiers, as we established earlier, up here, order does matter. So between 2 statements, it does not matter, but between 2 quantifiers, it does matter. And we can say that this is just equivalent to B or A, and we can say B and A and B is equivalent to B and A. And now similarly, A or B is equivalent to B or A. That's pretty straightforward, does not need much explanation. Now we have associative laws. And what this just states is that suppose we have three what's it called? Suppose we have three statements, right? So we have A and B and C, right? Keep in mind, these are all the same quantifiers, and this is going to be different from what I'm going to discuss next. These are the same quantifiers, okay? So we can rewrite this as A and B and C. Again, not same quantifiers. They're like either both. They're all conjunction, right? They're all and. There's no or and, right? There's no mixing. They're all the same. And similarly, we can say if we have A or B or C, this is logically equivalent to A or B and then or C. Again, same thing. This one's all disjunction. This one's all conjunction. Right? They're all the same, Now, distributive law. This is different. This is where you have different ones, right? So again, consider we have three statements, and we have, this time, we have something that looks like this. Again, look, we have one and we have one or. So this is where they mix and match. This is where they're the same. So this is where they mix and match, but this is done differently. So this is the same as saying these conditions, like if either of these conditions are met and this condition is met, right? So we can say this is the equivalent of saying A and B or A and C. And now if this doesn't make sense, consider this like if you're trying to factor something, right? So if I have this, right, the way I would expand this is I would do xy plus 4x, right? Because I apply this to each of the terms, like that, right? Exactly. So that's exactly how you do it. And similarly, if we have A or B and C, we would just do A or B and A or C. Again, the order of this doesn't matter. For example, I could say B or A and C or A, or I could say A, C, and A, B. It doesn't matter. Like the orders of the statements between the logical operators doesn't matter, but the order of the statements does. For example, quantifiers or other components of the statements, they do matter. And I believe that wraps up our episode for today. Thank you for watching, and next class I'm going to dive deeper into implications, converse, contrapositive, if and only if statements, and we'll take a look at a couple specific examples.